Hi and welcome to tutorial 10 on Dijkstra's algorithm, as this comes up in the EDEXCEL Decision 1 Maths A-Level module, but should be applicable to most other Decision Maths courses. For any other help with your maths studies, GCSE or A-Level, see HEGARTYMATHS or the website. Right, let's start by looking at what EDEXCEL says we need to know. Now, everything in green is what we've done in previous tutorials. In this tutorial, we're going to do Dijkstra's algorithm for finding the shortest path. Then we will have finished another sort of subsection of the EDEXCEL D1 course. Right, I want to start off by showing you a few problems I showed you when I introduced graphs to you back in tutorial 6, I think. So, I showed you this picture. I said let's zoom in. And I said on a weekly basis, let's say, I drive my Aston Martin from Milton Keynes to Cheshunt. How do I get there in the quickest way? Do I go along this route? Do I go along this route? Or do I do some sort of combination in between? How do I get there in the shortest possible distance, assuming those numbers are, say, kilometres between each of the towns? There's a problem that Dijkstra's algorithm we're going to learn about today solves for us. Now, in the case here, you could have a look at that and by trial and error get an answer, but it works, Dijkstra's, for much bigger problems. Let me show you another way how it might be used. Here's the world famous mountain, the Eiger, which until the sort of middle of the 20th century was thought to be unclimbable, okay? And since then, people have climbed the Eiger, but Dijkstra's algorithm, a way of finding a path, can be used for mountain climbing, and let me show you how. A lot of modern climbers might profile a mountain and work out a picture of it using technology, and then they may say stuff like, imagine on a path here, they may say, if I climb along here, say the climbing difficulty is of difficulty maybe 2, it's nice and easy, but then that leaves me with a climb up there of maybe difficulty, let's say 10. And they might be comparing it at that point to a more difficult climb here of, let's say, 6, but then a slightly easier climb here of 3. And along the way, they might use Dijkstra's algorithm or some form of it to climb to the top of a mountain. And for example, there's a very famous climber called Uli Steck who very recently climbed the Eiger in less than 3 hours, and I want to show you a quick video clip of him. It's very inspirational. It just either in his head he's using forms of Dijkstra's algorithm, or he may have pre-planned a bit of this sort of work to get up the mountain. Let's take a look.
Then after you climb this, you reach the point where you're into it. On one hand, you have in your mind you have to move fast, but on the other hand, you know exactly if I do a mistake, I fall off. And you see just more than 1,000-meter air below you, and you're like on this edge. out to the final snowfield. Now you have to get out of your body everything you can get as fast as possible to the summit. You just see your hands, your ice axe, and your crampons, and they have to just move. You're progressing on something, and that's all about. You want to keep moving, having a progress in your life. When you get to the summit and you push the watch, first you try to breathe a little bit, get some oxygen in your lungs. When I saw this time, I was like, oh, that's not possible. Just like, yeah, that was a good moment.
So that was a remarkable video there of Uli Steck climbing, but modern climbers do use some of the theories of Dijkstra's algorithm to find a route of least difficulty up a mountain, for example. So let's now introduce ourselves to Dijkstra's algorithm so we can go off and drive our Aston Martin on the weekends or climb mountains. So Dijkstra's algorithm finds for us the shortest path between two vertices or nodes in a network. Right, if we take a look at this, say we're starting at node S and we want to end at node T. How do I get there in the shortest way? Okay, now an easy picture like this, you could just work it out by trial and error, but Dijkstra's algorithm gives us something to work with when the problem's much more complicated. Right, and this is what Dijkstra's algorithm actually says. It has the following 7 parts to it, which I'm not going to read out for you now. I suggest you pause the video and copy them so you've got a copy of what Dijkstra is saying and you can refer to it as we do the examples. But the best way to explain this algorithm is to do an example. So let's move on to doing an example of Dijkstra. Here's the problem that I just spoke to you about before. Now, you may be shown the problem in that type of way, but in the examination, they will always convert this problem for you as follows. Now, they will create a box at each vertex where over here you put in the name of your vertex, S, A, D, T, B or C, etc. In the final value, you're going to put the weight it took you to get to that place, okay? And in the middle, it's the order in which you labelled that particular vertex. At the bottom, we're going to have some working. So this will be transformed into something like this. And that's the same problem. It just has the boxes as I talk about there below. So we're going to solve this problem, how to get from S to T in the shortest distance, using Dijkstra's algorithm. So let's have a go. Step 1. So what does step 1 say? Well, step 1 says, label the start vertex with a permanent label of 0 and an order label 1. So the order is 1 and the permanent is 0. What that's telling me is it took me, how far did it take, or how much weight did it take to get from S to this point? Well, we're already at S, so it took me nothing. And 1 is the first vertex I've actually labelled. Okay? And it's as simple as that. Okay, what does step 2 say? Step 2 says, having done that, you assign temporary labels to all the vertices that can be reached directly from the start. So, the vertices that can be reached from S are A, B, and C, and you put in some temporary labels, okay, temporary. Now, what you do here is you ask yourself, how much weight does it take to get from S to A? Well, it takes 5. What about S to B? It takes 6. And S to C, it takes 2. And you're done the next step. These are temporary at the moment. They may convert to permanent in a second. Okay? What does step 3 say? Well, step 3 says select the vertex with the smallest temporary label in your diagram and make this permanent and add the correct order label. Well, what's smaller out of 5, 6 and 2? 2 is. So therefore this is the second one I'm going to give a permanent label to. And how far did it take to get to here? It took 2. Right? And we've done step 3. Nice and simple. Right, step 4. Step 4 says the following. Now, what that's saying is put temporary labels on each vertex that can be reached from the one you've just made permanent. This is the one I've just made permanent. I'm going to assign temporary labels to anything I can get to from C. Well, I can get to B from C with another 2. It already took 2 to get here, another 2, so that's 4. Now, I write in the 4 because it's better than the 6 I previously got, and I cross that 6 off. What else can I get to from C? Well, I can get here by going 2 and then 12, so in total 14. I can't get anywhere else from C, so I'm done there. Okay? Now, in this case here, if by going up here, say that distance there had been something like 6, and to get from here to here had been 8, I wouldn't have written it in. Okay, I only write it in if it's smaller than the temporary label already there, and that's what this is saying here. Okay, right. Next stage now. Let's go on to the next stage. Okay, stage 5 or step 5 tells us to now select the vertex with the smallest temporary label and make it permanent. Okay, and then order it correctly. Now, what have we temporary labeled? There's a 5, that's a 4 currently, that's a 14. Which is the smallest? This one clearly here. So, it's going to be our third one that it's the third one in order, and it's going to have of weight to get there 4. Okay, so that's what stage we're at now. Next stage, step 6. Step 6 says repeat this until the finishing vertex T has a permanent label. So we're going to keep the process going. The one we've just made permanent, okay, we consider everything coming out of there. D, I could get to D from there with 4 currently to get to B and another 4, so it'd be 8. From B, I could get to T. It's already 4 to get there, another 8 would be 12. It's better than 14, cross out the 14, write 12. You can't get anywhere else from B that hasn't got a permanent label on it already. Okay, so at this stage, what you do, out of everything that's temporary, you consider the smallest. What's smaller out of 5, 8 and 12? Well, 5 is. So it's going to be the fourth one you label up, and it's going to have weight to get there of 5. Right, you consider everything you can get to from A. You can get to D. Well, you can get to D in another 4 on top of the 5 you've already got, but that's not better than 8. That would be 9, so we don't bother writing it. You can't get anywhere else from 8. So, out of D and T, which is smaller out of 8 and 12, well, 8 is. So that's going to be the 5th one we label, and it's going to have weight of 8. Then you consider everywhere you can get to from D. Well, I can only get to T via this way. Okay, so that would be the 8 I've already got and 3 be 11. It's better than 12, so I write it in. And therefore T is the 6th one I've labelled, and it had a weight of 11. So lastly, we move on to step 7, and that says we need to now find our shortest path. We've done all the algorithm. We need to find our shortest path by starting at the end vertex, retracing your steps to the start, and then stating your route and its length. How do you do that? Well, at T here, it took us 11 to get here. Which of these paths into T did I take? Well, 2 and the 12 is not 11, can't be there. 4 and 8 is 12, it's not 11, can't be there. 8 and 3 is 11, so I must have taken in that route to get into T. So highlight it. Same here. 5 and 4 is 9. Can't have taken that route because it's got to be 8. And 4 and 4 is 8, so I must have taken that route. Okay, from here now, what did I take? Well, 11 and 8 is not 4, so no. 0 and 6 is not 4, so no. 2 and 2 is 4, so I must have taken that route there. And lastly, the only route I could have taken was this one here, because there's only one path coming out. Right, so I went S first, then C, then B, then D, and then T. So I went S, C, B, D, and T, and it was of length 11. Make sure when you're doing your Dijkstra's algorithm, you do draw in the end route and you state the route and the length. Otherwise, you've done a problem, but you haven't actually solved it. So do make sure you do that. Last thing to state, therefore, at the end, there's a couple of extra points I wanted to state to you. Here's my final picture. Dijkstra's algorithm, having done this picture, it also finds for you the shortest route between the start and any point. What's the shortest route between S and D? 8. S and A, 5. S and C, 2. This number here tells you the shortest route from the start to that number, to that letter or vertex. So it does that for you automatically. And lastly, just be careful if there's a digraph in the network. Here, I've just changed it around. I've drawn an arrow here, okay, and what that's saying to you is, from my starting point S, okay, I couldn't have gone along here to A with length of 5. It was going against the way the arrow is. It's like a one-way street. I can't take that. So don't consider it when you're assigning your temporary and permanent labels, etc. So do be careful of these. Now at this stage, I think the best thing to do is to have a go at a few examples. I'll put in the question up. You pause the video, attempt the question, and then mark your work against mine in 10 seconds. So take a look at this. I'll stop talking, and in 10 seconds I'll go through the answer. Right, first thing I do is labeling all the vertices. That was A, B, C, D, E, F, G, H, I, and J lastly. This question says start at A and you want to end at the ring vertex, which is J. So I want to end at J. Right, first thing I do is in here I say that's the first one I label and it's got a 0 weighting to get from A to A. Everything that comes out of A I assign temporary. So that would be a 4, that would be a 17, and this here would be a 10. Okay, look at all your temporary labels, which is the smallest, this one. So label it, the second one you've labelled permanent with weighting 4. Now you consider everything that comes out of B. Well, I could get to E here in 4 plus 2, which is 6, so that's better than 10. I could get here in 4 plus the 14, which would be 18. And that's all I could get to from B. Look at all your temporaries. What's smaller out of 18? 6. And 17? Well, 6 is. So that's the third one you make permanent. And it's of weight 6. Now you consider everywhere you can get to from E. Could go up here in 11 plus the 6 you've already got 17. That's equal to the best we've got currently. You could go down here in 18, which would be 6 to get here, and 18. So that would be 24. You could go along here with the 6 and the 8 of 14, and there's nowhere else you could go to. Look at all your temporary labels, 18, 17, 24 and 14. Which one's your smallest? Well, 14 is, so that's going to be your fourth one of weight 14. Okay, consider everything you can get to from H. Could go back here in 14 plus 16 is 30, no good. Okay, could go along here in 14 plus 15, which is 29. Okay, could go down here in 14 plus 3, which is 17. And that's it. Can't get anywhere else here that would do any better. Now consider all your temporary labels. What's smaller out of 18, 17, 24, 17 and 29? Well, 17 is the smallest. There are two of them. You can choose any. At that stage in your algorithm, if there are two the same, choose any. So why don't we choose this one? Okay, let that be our fifth label, and it's of weight 17. Now you can see where you can get to from D. Okay, I could get along here in another 1 plus 17, which would be 18. I could get along here in another 16, but that, sorry, don't count that because this is already permanent. There's nowhere else I could get to from D that to somewhere that isn't permanent. Okay, so therefore, what's smaller out of all these? Well, this 17 is still the smallest, so that must be the sixth one, and I label that 17. Okay, from here, where can I get to? Could get up here, could get along here in another 7, so that would be 24, which is better than 29. Could get along back here, 17 plus 9, which would be 26. It's not better than 24. So they're all the possible options I can do. The best of my temporary labels now, I've got 18 here, 24, 18. Okay, it's definitely 18. So why don't I call this my next one here? So this would be the seventh one and of weight 18. Where can I get to here? Well, the only place I could go that's temporary at the moment is along here another 10, which would be 28. That's not better, so I don't write anything in here. Consider all my labels here. I've got 24, 18 and 24. The smallest is clearly the 18, so that must be the eighth one I label with weight 18. Consider everywhere I can get to from here. Well, I can only get along here, which is another 12, would be 30. It's not better than 24, so I can't write anything in. And the best out of these two, well, why don't I just state this? Why don't I just do this one? It doesn't matter. That one's 24, so that would be the ninth one of 24. And I can't get anywhere here that's any better, and this would be the 10th one of weight 24. Okay, and I've carried all of that out there, but now I must work out what path it was. So, starting it here at 24, 18 at 12 is not 24, okay, 14 and 15 is not 24, okay, 17 and 7 is 24, must have taken that route. So we're at 17 here, okay, and the only option to get there in the correct would have been from here, because 14 and 3 is 17, so it must have taken that route. From here, well, it can't be here, it's got to be here. That's the only one. Must have taken that route because 8 and 6 is 14. From here, how did I get here in 6? Well, not there, not there, not there. It must have been along here. And last one must have been up here. Okay, so this was my shortest route. And state what it is. Well, it's A, B, E, H, I, and J. And it has weight in total 24, so weight 24. The route and the length is the route is A, B, E, H, I, J, and it's of length 24. Okay, next one. Have a go at this next question. Be careful here. There's digraphs involved, so just take a look at the next one. Pause the video, attempt the question, and mark yours against mine. I'll go through in 10 seconds. Okay, we're starting at A. Okay, we're starting at A and we want to end at the ring vertex, which is G. Do notice this arrow tells us I can only go along that direction. This arrow says I can go there, this arrow there, this arrow back. So there's a couple of arrows going involved. Where there's not an arrow, you could go either way. Okay, start off, that was A, B, C, D, E, F, and G. Okay, and then this is my first point, and it's got weight 0 to get there. Okay, because you're already there. Then consider all temporary labels. I could go up here in 6. I can't go along here, no, but I could go along here in 3. What's smallest out of these two? Well, this one is. So it's the second one and of weight 3. Where can I go to from here? Along here, which would be another 20, so that would be 23. I can't go along here actually, no, I cannot go along here, so therefore that's the only place I can get to. The smallest out of my temporary labels is therefore this one, which is my third one, and it's of weight 6. Where can I get to from here? Well, I could go along here in the 6 and 11, which would be 17, which is better, or I could go along here, which is 6 and 5, which is 11. Okay, now I consider which is the smallest out of everything I've got. Everything I've got here is a 17 and 11, that's the smallest, so it's the fourth one I label of weight 11. Where can I get to from E? Well, I can't go along here, it would be going the wrong direction, but I can go to along here, which would be 11 and 9, which is 20. Okay, and at this point now, I look around to see what my smallest is. 17 and 20, this is my smallest, so it's the fifth one I label, and it's of weight 17 at that point. Okay, and then I ask myself where I can get to from here. Well, the only places I could go from here to temporary places, I could go along here, which would be another one, which would be 18, or I could go along here, which would be 17, 17, 34, to this point, which is not better. So I look at all my temporaries, which is smaller, 18 and 20. Well, the 18 is, so that's the sixth one I label of weight 18. And from the one I've just called permanent here, where can I get to from here? Well, along here with another 14, which would give me 32, which is not better. So therefore, this must be the seventh one I label, and it's of weight 20. Okay, and finally you just end by stating your route. So I start at the back. How did I get to here? I must have gone along here, because 11 and 9 is 20. What about from here? Well, I must have gone along here, because 6 and 5 is 11. And here I must have gone along here, because 0 and 6 is 6. So my route here was A, B, E, and G, and it had weight of 20. Get to ensure you write your route and the length at the end of the question. Finally, to finish, here's some questions to do further. I would suggest you read chapter 3, page 51 to 58 and look at the examples, in particular on digraphs, because I just mentioned them here, but there's a few good examples there. And exercise 3D on page 56, I suggest you do all questions. Last thing then I suggest you do is you go to the past paper questions 10 video. It's going to look something like this. It's going to be on Dijkstra's algorithm, some of the past paper questions that came up, so you could practice the theory you've just learned on the exam questions. I hope you found the following useful in your work on Decision Maths 1. Thank you for watching, and tune in next time.